Welcome back. This is the Lord's Made. Glad I should dress me glad in it. In this video, I'm going to talk about entropy. So, entropy is the idea of how much disorder is inside of a system. So, how messy is the chemistry lab? How messy are the molecules that make up the substance? All right, so it's this idea that you could have some disorderness related to the system. Okay, so really it's a probability game how the energy is distributed. As the energy gets more and more spread out, you get more and more disorderly. So if all the energy is in one place, it's very orderly. If energy is spread out or it's random all over the place, then it is disorder. So we use the letter S for entropy. So if we have an entropy increase, that's increasing disorder, we'd have a positive S. If entropy goes down for the chemical reaction, we'd have a negative S. So again, this all we're saying here is that if you have a positive S, this means that the reaction is going to make it more disorderly. If you have a negative S, that means that the reaction is going to make it more orderly. Generally, reactions tend to be spontaneous, or meaning that are likely to happen if it has a positive S. So if we have an increase in disorder, this is no different than saying, is your room more likely to get dirty or get clean? It's more likely to get dirty on its own. Is my kitchen going to be getting clean on its own, or is it going to get dirty on its own? Well, with 4 kids, it doesn't take very long. I sweep the floor, and it's already dirty again. So the universe tends towards disorder. We tend to have reactions take place that cause things to get messy. You know, you buy something brand new. As soon as you buy it brand new, what happens? It starts to degrade. It already starts to break down. You know, that brand new car is only brand new for a split second. As soon as you drive it out of the lot, it's no longer brand new. You buy that brand new cleaning rig, and as soon as you use it one time, it's dirty for the rest of its life. All right. So basically the idea is things tend to get more disorderly, things break down. That's basically the second law of thermodynamics in a nutshell. So anyway, when we look at the data tables, so they'll have enthalpy values, entropy, Gibbs energy too, haven't mentioned that yet, but it's going to have enthalpy and entropy values. So for enthalpy, the values on the periodic table were standardized as 0. We said, let these things be 0. Entropy was not defined as 0 because they're not all the same. All right, so although we should mention that if you care to know, when is entropy 0? At absolute 0. If it gets down to absolute 0, nothing moves. We know exactly where you are. All right, but if you're moving at all, we don't know where you are, so there's a little bit of randomness to where you are. So in any case, elements on the periodic table for entropy are not 0. It depends on what state of matter they are, because if you're a gas, you're very disordered. If you're solid, we know where you are. So, and just mention again, it's at these conditions. And you should also know too, when you're doing some math in this class, especially on those A-level questions, keep an eye out, because enthalpy is measured in kilojoules per mole, entropy is measured in joules per mole. So when you're doing some math, these things later on, make sure you convert one to the other one. Either take the kilojoules to joules or joules to kilojoules. So some quick notes about what makes things more disorderly. Some general rules about whether disorder is increasing or decreasing. In general, if you have a solution become more dilute, that's going to increase the disorder. All right. So you increase disorder when solutions get more dilute. So if you add some water to a solution, it's going to make the molecules inside there that were dissolved into there more spread out, and you don't know where they are. The odds of you finding that molecule you wanted have gone down. All right. Which is saying that, if I drop a marble into my home swimming pool, could I find the marble? Probably. If I drop the marble into the lake, am I going to find it? No, because now it's more spread out. There's this bigger area, and so we're going to have a less likely time to find it. If gas pressure goes down, that also causes things to get more disorderly, because then things can spread out more. If you reduce the pressure, the gases that were making up that system are going to spread out more, and that makes them more disorderly. They're more random. They're further apart. They're more dispersed. When the number of moles of gas goes up, you also get more disorder. So in this equation here, we have one gas molecule breaks apart into 2 gas molecules. Well, now we have 2 gas molecules. That's like having, we used to have 1 kid, now we have 2 kids. It's twice as crazy. All right, so if you have more gas molecules, that's like having more kids to watch, and that's going to be crazier time for you. It's going to be more disorderly. When temperature goes up, that also causes things to get more disorderly, because if things are warmer, the warmer things are, the more they're moving. And the more they're moving, the more disordered they are, the more chaotic it is. All right, so anytime you heat something up, disorder is going to go up. And again, general rule, gases are more disordered than liquids, which are more disordered than solids, which is to say that if you leave a baseball somewhere as a solid, you can come back to that baseball and find it anytime you want to. Oh, it's right there. The solid stayed right where we're supposed to be. The molecules themselves even stay in the same place. But if I took a baseball made of gas and left it there, it would spread out and it'd be gone. All right. So the general idea is gases are constantly moving, so they're very disorderly. So solids are very orderly. Liquids are second place. Aqueous, again, that's the idea that you put something into a solution and it starts spreading out. That's going to be more disorderly than a liquid, but still not as disorderly as the gases, who are the kings. And often when you look at a chemical equation, all you do is count gases, because gases are the crazy kids. All the solids and liquids, they're pretty orderly. They know where they're supposed to be. The solid stays put. The liquid, it moves a little bit, but it stays in its relative shape. But gases, they are totally different. They are all over the place. So when you're getting questions like which one has the most disorder, which one do you expect there to be more entropy with, basically, first consider state of matter. State of matter is more important than anything else. If you're a gas, you're disorderly. If you're solid, you are orderly. So solids are orderly, gases are disorderly. So even your oven, you turn your oven on up to 425. Now that metal is really hot. It's, you'd burn your hand touching it. But it's still more orderly than the oxygen, because the oxygen's flying all over the place. The oven stays put right where it's at. Nice job, oven. So even though you got warmer, you're still orderly. So, all right, so let's take a look at some reactions on here. Do they have a positive S, meaning that it's gotten more disordered, or a negative S, meaning that it's more orderly? So what you can really do is just count gases. On the left side, there's no gases. On the right side, oh, we have a gas. We are more disordered on the right side. So this is an increase of disorder. We have a positive S. This reaction has a positive S. Why? We have more gases on the right side. Next one, solid. We have table salt as a solid. We pour it into the water and it dissociates into ions. Now we have aqueous sodium chloride. So solid's more orderly than aqueous things. So this has a positive S as well. We're going to increase the disorder. The salt used to be staying still right in that pile. Now the salt's mixing around with the water. We don't know where it's at. Here, sodium plus chlorine makes sodium chloride, making the table salt. On the left side, we have a gas. No gas on the other side. That is a negative S. We're getting more orderly. We took a very disordered gas and made it a solid. Now that means we've gotten more orderly, so that's going to be a negative S. Here, we have gas on both sides, so we're going to actually count that actual number of gas molecules we have. We have 3 hydrogens, 1 nitrogen. That makes 4 gas molecules on the left. We have 2 ammoniums on the side. So we went from 4 gases to 2 gases. So we have less gas, so that's going to be a negative S. We got more orderly going from the left side to the right side. And for this last one, we have 2 gases on the left, 2 gases on the right. Here, we're unsure. We'd have to actually calculate it. We have to actually go to the data table and look at the numbers. So how do you calculate those things? You calculate them the same way that you calculated the last thing with enthalpy. It's just products minus reactants. So to calculate a change in entropy, the same way we did for enthalpy, you just take the products values and subtract the reactants values. So as an example up there, we had table salt turning into dissolved table salt. If you look at the data tables, you'll find that table salt has a positive S value of 72 joules per mole as its disorder constant, how much disorder is associated with that substance. When it's dissolved, it has a value of 115. So to find the change, to find whether it's a positive or negative S, we would just take the products value, 115, subtract off the reactants, and we end up with a positive 43 joules per mole there. We're basically saying this is a positive S. It gets more disorderly. How much more disorderly? This much more disorderly. Now, do take note that if you had multiple ones, you just multiply it through. So if we had 2 NaCls turning into 2 NaCls that are dissolved, we would just multiply everything by those numbers. So it'd be 2 times 15, 2 times negative 72. And so it's just proportional. So, all right, so again, big idea, disorder. S is disorder. S is all about how random are the molecules. Are they orderly or disorderly? So a positive S means that you're getting more disorderly. Again, that's how the universe tends to work. The second law of thermodynamics says things get more disorderly, things break down. Generally, most reactions that take place on their own tend to have a positive S value. A negative S is when the chemical reaction makes things more orderly. All right. We could also connect this to state of matter. Going from solid to gas, that is making something more disorderly. going from a gas to a solid is making more orderly. God's peace.